Have you ever watched a sprinter just explode from the starting blocks and thought, wow, how do you even begin to describe that? Well, it's not just poetry, you know? It's physics, and today we're going to break down the language of motion. We'll look at the core ideas that explain how literally everything moves, and we'll do it all by looking at one single, powerful sprint. Let's jump in.
So to make this all feel real, let's follow a runner. Picture them right at the starting line, ready to go. They're going to run 100 meters in just 10 seconds. Every single thing we talk about today, from where they are to how fast they're going, we're going to see it happen through their race.
All right, so where do we even begin? Well, before we can talk about speed or anything fancy like that, we have to know the most basic thing of all. Where is our runner? It sounds almost too simple, right? But in physics, being super precise about location, well, that's the foundation for everything else.
So what exactly is position? It's the answer to the question, where is it? But, and this is the important part, it's always relative to something else, a reference point that we choose. For our runner, the most obvious reference point is the starting line. We'll just call that 0 meters. From now on, every other spot on the track is measured from there.
And bang, the starting gun fires. Our runner just takes off, flying down the track and covering the full 100 meters to that finish line. They've just traveled a very specific path. And the length of that path, well, that brings us to our next big idea.
Distance is, well, it's pretty much exactly what you think it is. It's the total ground you've covered. A great way to think about it is like the odometer in your car. It just counts up and never goes down. So for our runner's sprint to the finish line, the distance they traveled is a nice, clean 100 meters. Easy enough, right?
Okay, so the race is over, our runner catches their breath, and then they turn around and just walk the 100 meters right back to where they started. And this is where things get really interesting. This is where physics makes a super important distinction.
Okay, check this out. We have distance versus displacement. We already know distance is the total path, the whole journey. Physicists call this a scalar. It's just a number. But displacement is totally different. It couldn't care less about the winding path you took. It only cares about the straight line from where you started to where you ended. It's a vector, which just means it has a number and a direction.
So let's put this to the test. Our runner covered a total distance of 200 meters, right? 100 there, 100 back. But think about it. They started at the starting line, and they ended up back at the starting line. So what was their final displacement? 0. Yep, 0 meters. Because their final position was exactly the same as their initial position, their overall change in position, their displacement, is nothing. They went on a 200-meter trip just to end up with 0 displacement. And that is the whole idea in a nutshell.
Okay, so we've totally nailed down where our runner is. Now we can ask the next obvious question, how fast are they going? And just like we had 2 ways of talking about location, physics has 2 different ways to talk about how fast you're going.
First up is average speed. This is the one we all use in everyday conversation. You just take the total distance you went and divide it by how long it took you. For our runner's big sprint, that's 100 meters of distance divided by 10 seconds. That gives them a seriously impressive average speed of 10 meters per second.
But then you have velocity. And if you remember that displacement was all about direction, you can probably guess what's coming. Average velocity is your total displacement divided by time. And because it uses displacement, that means velocity also has both a number and a direction. It's another vector.
And this slide just lays it out perfectly. Speed is just a number. It answers how fast. So, 10 meters per second. Velocity answers how fast and where to. So it's 10 meters per second towards the finish line. See? That little bit about direction makes all the difference. But wait a minute. Our runner didn't just instantly appear on the track already moving at 10 meters per second, right? Of course not. They had to start from 0 and build up to that speed. And that process, that act of changing your velocity, that's what physicists call acceleration.
Now, this is a really, really important point. Acceleration is not just speeding up. It is any change in velocity. So yeah, speeding up is acceleration, but guess what? Slowing down is also acceleration. Sometimes we call it deceleration, but it's the same idea. And get this, even turning a corner while keeping your speed exactly the same is still acceleration because you're changing your direction.
So how do we actually measure it? It's really just a simple 3-step recipe. First, you look at the final velocity. Then you subtract whatever velocity you started with. And finally, you divide that change by how much time it took. That's it. It just tells you how quickly your velocity is changing every single second.
All right, numbers and definitions are great, but sometimes the best way to really understand the story of what happened is to see it visually. Think like a coach. A coach might use graphs to analyze their runner's performance, and these graphs are the perfect way to see all these ideas in action.
First up, we have the position time graph. This thing is basically a play-by-play of the runner's location, their position, at every single moment in time. So here's how you read it. The up and down axis, the y-axis, shows their position. The side-to-side axis, the x-axis, shows time passing. But the real magic here is the slope of the line. The steeper the line, the more ground the runner is covering in less time, which means they have a higher velocity.
Okay, next up is the velocity time graph. Now, instead of plotting their location, this graph shows us their velocity at every moment. This is where we can really see that amazing burst of acceleration right at the start of the race.
And this one tells us two incredible things. First, the slope of this line is acceleration. So that steep upward slope at the beginning, that's our runner getting faster and faster. And second, if you calculate the total area underneath that line, you get their total displacement, how far they actually went. How cool is that?
So what about when our runner was walking back to the start? They were probably moving at a nice, steady pace, right? In physics, we call that uniform motion. And on a velocity time graph, that just looks like a flat, horizontal line. Why? Because if your velocity is constant, your acceleration is zero, and that means the slope is zero.
So let's do a super quick recap of the big ideas. Distance is the whole journey. Displacement is just from start to finish. Velocity is just speed that knows where it's going. Acceleration is any change in that velocity, speeding up, slowing down, or turning. And finally, graphs are an awesome tool for telling the complete story of an object's motion.
Okay, so we've pretty much mastered motion in a straight line. But what happens when things get a little more curvy? Think about a race car going around a corner. Its speedometer might stay locked at a constant speed, but its direction is changing every single second. So, is it accelerating? Based on what we just learned today, you already know the answer to that. And that's where the physics of motion gets even more fun.